All right, so with section 10.5, we're going to be taking a look at area and arc length. And area and arc length are things that we did look at in Calc 2. We're looking at them in relation to polar coordinates, which is not something we've done before, okay? So first of all, here's the idea. So we're going to want to compute the area enclosed by a polar curve. Since the graph of a function since the graph is not a function of the form y equals f of x, we can't use our normal area formulas. So if you remember back from Calc 1, what we do, sort of conceptually, is we make these little bitty rectangles, right? From the axis down to the y-axis, or from the curve down to the y-axis, or x-axis, get the right axis in there. And then we make the areas, or the widths of the areas go infinitely small, right? And that sort of fills in the gaps. Well, we can't do that because we're not dealing with functions in the form y equal f of x. So while we could convert the formulas from 10.2, right, the ones in polar coordinates back into rectangular and so forth, there is a simpler approach that uses the following geometric argument. Okay, so if you're a writer of all the things, you're not going to want to write all this down. This is a huge, look at this. You see everything that's typed on this paper? Okay, so fill in your gaps later. Just pay attention and follow along if you will. So I want you to remember that the area of a circle with center, the area of a circle with radius r and central angle theta is area equals pi r squared. Everybody remembers that, right? Basic geometry stuff, right? From probably about 7th grade when you start first encountering this. And if we do a sector of a circle, so think piece of a pizza, right? That's a sector. If you do a sector of the circle with a central angle theta, it will involve a ratio of the sector of the circle. So you take theta and you divide by 2 pi. That gives us a ratio of the angle, right? A portion of the circle. So the area of a sector is actually found by taking area equals pi r squared, multiplying it by this ratio factor, whatever this ratio is, whatever your central angle is in radians, divided by 2 pi. And that simplifies to 1/2 r squared theta. Okay, so that typically comes up in a geometry course or a trig course. My trig class did it earlier this semester, okay? They saw that formula. Now we're going to consider the area enclosed by a polar curve that's defined by r equals f of theta. And the rays, theta equals alpha and theta equals beta. And I will draw a picture, so hold tight. Where f is continuous and positive on the interval from alpha to beta. Okay, let me figure out where I am here. We'll draw a picture in just a second. Let me get a little bit more in this. Okay. Yeah. Then, in the same way that we partitioned the area into rectangles when we worked in function notation, right? We can partition this area into sectors. So think about making thinner and thinner slices of the pizza, right? So you have a slice of pizza and you're making the sectors themselves infinitely thin, just like our rectangles were infinitely thin. The width of each subinterval then is delta theta, which is theta sub I minus 1. It's beta minus alpha divided by n. N is the number of subintervals. On each subinterval, we approximate the curve with the circular arc r equals f of theta sub I. All right, let's draw a picture. I've got space right here. You've got a blank spot if you've printed out the notes in your spot right there too, to the left. And so this is a good place for us to draw our picture in of what's happening here. So we've got some arbitrary curve over here. So it looks like something over here, whatever it is. It doesn't have to look like a circular pizza. That's the whole point, right? And there's an arc that goes from alpha here to beta. So this one right here is my alpha. This angle right here is beta. Everybody good so far? So the sector that I'm looking at right now is right in here. So it looks like a piece of pie with an arbitrary edge, not a circular edge like our pizzas normally would be. And if we spliced this, in half, and then in half again, and in half again, and half again, that process would be similar to what we did when we made our rectangles. We took our interval, and we cut it in half, and we did half, and we did half, and we did a whole bunch of halves of things back in chapter 4 when we did this. And we took a section of material where you actually computed all those areas and added them together. Do you remember doing that? We're not doing that with the sectors. but that's the motivation, that's the idea behind it, right? From there, in Calc 1, we moved on to finding out the fact that, okay, but we can do this exactly with integrals, and it will work much quicker, and it will be exact, right, instead of doing this approximation method. So a little bit more with the approximation idea before we move on from here, but we're not going to actually make these calculations, okay? So then the area, A sub I guess my picture is supposed to go there. We'll move it there. We'll just put it in there too. There we go. Then the area A sub I enclosed by the curve on this subinterval is approximately the same as the area of the circular sector of radius f of theta sub I and central angle delta theta. A sub I then is 1/2 r squared times delta theta. It's 1/2 of our function squared, right? That's the radius, is the same as our function squared, delta theta. And the total area enclosed is approximately, there's that key word showing up in, I mentioned before, approximately, right? The sum that we would get by adding up all these little tiny sectors. So I equals 1 to n of the areas, which is 1/2 f of theta sub I squared delta theta. And if you remember, we used this same idea when we went into this notation in functions, and we replaced our summation with an integral symbol. And we don't have to go from 1 to theta anymore. It uses the limits of integration. In this case, it would be the alpha and the beta angles that this is talking about as our limits of integration. And we would be able to use antiderivatives to actually find this exactly. And that's exactly where we're headed. So as long as we do this numerous times, infinitely many really, we can improve the approximation by making n larger, right? You make more and more and more and more sectors, which makes the sectors thinner and thinner and thinner and thinner. And as the limit, taking the limit as n goes to infinity, then we would have this integral over here on the right that feels much like the things we were doing in chapter 4. We have that same area formula. It's 1/2 r squared theta. R squared times theta. That's what it is. But we have d theta because our interval is narrow, right? That's what's going to 0. And we have our alpha and our beta as our limits of integration. We're about done with all of the writing of notes. Okay, we're really close. There is a theorem then that this is all leading up to. So all of this is sort of motivation to get to the point of finding this formula. And then our theorem itself actually says what we just did. So if f is continuous and non-negative on the interval from alpha to beta, and beta minus alpha is less than 2 pi, so it's a positive angle less than 2 pi, then the area of the region bounded by r equals f of theta from alpha to beta is that the area is 1/2 the integral from alpha to beta of f of theta squared d theta. Or you could say the area is 1/2 the interval from alpha to beta of r squared d theta. Those aren't different formulas, they're just different ways of thinking about the same formula. Okay, so you're going to want your calculator out for what we're going to do next, okay? At least as a reference point. You may or may not use it directly. We'll see. But what we're going to do is we're going to take formulas that are in polar, right? Polar formulas. And we're going to find the area of the region that they indicate. Typically speaking, they don't tell us what alpha and beta are, okay? That's important for you to realize that we're going to have to figure out what alpha and beta are. And having our calculator as a support to verify, even if we think we know what they are, to verify it visually can be very helpful. So this one says we're going to take one leaf of the equation r equals cosine 3 theta. So if you take your calculator, there's a lot of really interesting formulas. We've talked about this in a previous section that show up in polar that we never got with function notation. So move this back in. If you graph, let's see, cosine of 3 theta, and you might think, kind of like what we've done before, well, what kind of angles for theta make sense? Well, if theta, normally for cosine, has a period from 0 to 2 pi, and we have a 3 on ours, what would our expectation be for our period? So normally a period for 2 pi is 2 pi for cosine of theta, but I've got 3 theta. So what would the period be if I were doing this? Think back to trig. What would we do, Sophia?
6 pi.
Close. We don't want to multiply it by 3, we want to divide it by 3. Okay? So if we go 2 pi divided by 3, this should give us the entire image of cosine 3 theta. So if you take your window and you go from 0 to 2 pi over 3, we should get the entire image on this screen. I've got my t-step still at 0.01. I think I'm going to change it to 0.1 just so I can see a graph a little quicker. If I can always change it back if I need to. This is a graph of cosine. Cosine in front of it has a number 1 here. So I don't need this going out very far. Right now my screen says negative 10 to 10. I think that's definitely overkill. So I'm going to make mine go from negative 2 to 2 on x min and x max and y min and y max. And I'm going to graph it. Okay. Now in doing so, mine looks like this right now. It looks like it did that. Did yours do that? Yeah.
Well, it did that, and it also made it go further, and it gave me a more full image.
Yes. So our anticipation of this being 2 pi over 3 ends up not being quite right. Okay? So Adrian, what did you let yours go out to?
I had the 3 pi.
You went out to 3 pi.
Yeah.
Let's try going just out to 2 pi and see what happens, because I think that might be enough. Oh, it's more than enough. It still kept going beyond that. Did you just get pi?
It's just...
Okay, and we have pi, so our window going to pi, we think we need just pi. I think so. So our window actually only needs to go to pi. So from 0 to pi is where we are. Now, whoops. It's theta. Now that's not alpha and beta, by the way. This gave us the whole image. But this description does not say I want the area of the whole image. It says I want the area of one leaf. So I want 1/3 of the picture that my calculator currently shows. So right now the picture looks something more like this, right? Fan blades or something like that. And I only want one of those leaves. So how do we deal with that? Well, I'm going to show you how to deal with that, not from a trial and error perspective, like we're looking at this to get this whole thing to graph, but a more concrete algebraic or trigonometric kind of perspective. So what we're going to actually do is we're going to set our cosine of 3 theta, and we're going, let me move this to the side. We're going to set that equal to 0. And the reason we're doing this is because at the origin, remember we're doing r and theta, r is equal to 0. Okay, origin r is equal to 0. So I set this equal to 0, then this 3 theta has to equal something. So now you know how to think about the cosine graph. Where on the cosine graph do you have cosine values that are 0? Okay, pi halves and 3 pi halves. So if you're thinking unit circle, you should be thinking, that's a terrible axis, but you should be thinking these locations approximately, right? These are the cosine values. You can think of it in terms of the graph of cosine too, if you want to think about like the actual like sinusoidal graph that bounces up and down with with cosine. So this is going to happen at pi over 2 and 3 pi over 2. Okay, and it keeps going, 5 pi over 2, 7 pi over 2, and so forth. So let me put that down here. But we want to know values for theta, so what will I have to do with theta? I'll have to divide it by 3. So this is pi over 6, and then 3 pi over 6, which, yes, I realize that simplifies. But this is how we would solve that. Okay, does it make sense? All good so far? Okay, so let's see what happens if you make our window now that goes between these two values. So we're going to have our window, our theta minimum is going to be pi over 6, and our theta maximum will be 3 pi over 6, or if you want, you can write it as pi over 2. And it might surprise you which of the petals it graphs, but I think it does graph just one petal. Did it? Where did the petal show up? In the third quadrant, right? Does everybody see that? Okay, great. So as we're setting this up now, we have found the limits of integration, which is like really the hardest part of doing this, okay? So our formula, our area formula, is 1/2 the integral, and we have pi over 6. You can write 3 pi over 6 or pi over 2 as your upper limit of integration. And then this is the equation cosine squared. Well, it's cosine of 3 theta, and then it's squared, d theta. Okay, is that all right with everyone? Okay, you are going to need a power reducing formula. Okay, do you remember what those are? Okay, so it's a formula from trig. I'm about to teach mine on Wednesday, actually, power reducing formulas, so that's kind of a interesting timing of that. But the power reducing formula comes from your trig table. I think I have the trig table with me to show you it exactly. Let me see if I do. It's not on that one. So I don't have it with me. I don't have the second page, I only have the first page. All right, so let me write down. Let's see if I've got it written in my notes well enough to see it. The power reducing formula says the following. If I have the cosine squared of theta, then this is equal to 1/2 of 1 plus the cosine of double the angle, like that. Or you might be more familiar with it being written like this. That's how I think it's written in my trig book, where they put that over 2 like that. I kind of like it out in front better, so I'm going to leave it there. Okay? So I will double check that the one that's posted inside of our classroom has the power reducing formulas, but you can just Google it too, right? Power reducing trig formulas, and they're going to come up. There's power reducing formulas not just for cosine squared, but there's also ones for sine squared, and so there's both of them there. But they all involve bringing about the formulas that double angles. They're a connection to the double angle formulas. Now notice what happens here. Whatever this theta is, it's doubled here. So our theta is not theta, it's 3 theta. So when we double it, we're going to get 6 theta. Make sense? Okay, you're going to double whatever angle you have. So with ours then, we already have a 1/2, but we're getting another 1/2. We still have pi over 6 and pi over 2. But now we're going to have 1 plus the cosine, and it's of 6 theta, d theta. We have to get that power out of it, all right? Our ability to take derivatives and antiderivatives with sines and cosines is going to depend on us not having powers of sines and cosines. We don't want powers there, okay? So it's important that we are able to reduce those. And you guys encountered this in trig, or in a Calc 2 as well. It was one of our methods that we did in chapter 8 when we were trying to get rid of powers. I mean, like it was it was in the trig section of 8.4 or something like that. So we have done this recently-ish as well. Just not quite as, not with R, basically. Okay, so we've got a 1/4 now because I got 2 1/2. And we have our interval from pi over 6 to pi over 2. Before I write my interval notation, I'm going to put it at the end. Let's actually take the antiderivative. So what's the antiderivative of the 1? What is it?
Theta.
It's going to be theta. I just couldn't hear you very well. And then what's the antiderivative of cosine? Generally speaking, it's positive sine. Yep, your antiderivative of cosine is sine, but we do have the sine. Oh, I'm off screen. No wonder. I'm like, why isn't it not writing anymore? Let's just move it over. Sine of 6 theta, but we really have a u substitution there. It's not a very exciting one, right? It's just a constant u substitution, right? Our u here is 6 theta, and I would need to divide by 6, right? So our theta is equal to 1/6 of u. So this 1/6 showing up over here. So there's going to be a 1/6 that's going to show up in here with my 1/4 as well, but not out front with the 1/4. Right here is the 1/6. So the antiderivative of cosine of 6 theta is 1/6 sine of 6 theta. All good with that? Okay, and we're evaluating this at pi over 2 and pi over 6. So we already have our 1/4. I have pi over 2 plus 1/6 sine. 6 times pi over 2 would actually be 3 pi, right? And then all of this is subtracting off, putting in pi over 6. So I have pi over 6 and then plus 1/6 sine of pi. Did I get all my pieces in there right? I think I did. Is that all right? Okay. Sine of 3 pi. What is the sine of 3 pi? That one's 0. And what's the sine of pi? Also 0, right? So a lot of this is just going to collapse. I do still have a 1/4. I do still have a pi over 2 and a minus pi over 6. Oops, like that. So what is pi over 2 minus pi over 6? Nobody's going to talk to me. How about we get a common denominator? That work? Now what do I have over 6? 2 pi over 6. So I have a 1/4. I have 2 pi over 6, which will of course reduce. And if I simplify and so forth, I'm going to get pi over what? 12. Our area is pi over 12. Okay. We all right? Okay, we should try another one. Different equation, 1 plus 2 sine 2 theta. And we're wanting to find a larger loop. So we can play with this. We can manipulate a little bit. 1 plus 2 sine of 2 theta. We can at least let our window start with the 0 to 2 pi and see what happens. You might need your X-min and X-max to go a little wider because this one has a 1 plus a 2. I'm going to go from -4 to 4. I think that's probably going to be sufficient. We'll see. Oh, this is a good one. So the image is definitely not symmetric like the last one was in the sense that all of my loops are equal. I have a big loop here and a big loop here, and then I have these 2 tiny loops. Is that what yours looks like? Roughly speaking. So clearly it says it wants the larger loop, so it wants one of these, either this top one that I've shaded in or the bottom one. So as we take a look at this, we're going to do the same thing we did before. We're going to set this equation equal to 0. And we're going to solve. So for starters, this means then that sine of theta is going to equal -1/2. Is that okay so far? Subtract the 1, divide by 2.
Isn't sine of 2 theta?
Oh, did I miss my 2? I did. I left my 2 out. Thank you. All right, everything else look good? Okay. So we need to think about unit circle and where we get sine values that are -1/2. So let's start with the negative. Where do I get sine values that are negative, period? Yep, quadrants 3 and 4. These are sine values that are negative. Where do you get the ones that are -1/2?
5 over 6, 7 pi over 6, and -pi over 6.
Yeah, so these pieces right here, the ones that are really close to the x-axis, right? So this one here, going all the way back, is 7 pi over 6. That's the one that Preston said. The other one, if we go in the negative direction, would be -pi over 6. If you want to go in the positive direction, it'd be 11 pi over 6. Okay? So we don't necessarily know which one we need, so keep that in mind, that we might choose wrong. So Preston said -pi over 6, so that's the one we're going to try first. So this looks like -pi over 6, and then we would have 7 pi over 6. And there's more after it. They aren't at equal intervals like the last one, right? On the last one, they were pi apart, right? We were at the top of the unit circle, bottom of the unit circle, and it bounced forward and backward. I can't just go These are not symmetric, right? One of them is down here in quadrant 3, but it's not equally further, like it's not the same distance to go from the yellow on the left to the yellow on the right as it is to go backwards. Does that make sense to everyone? So when I put this comma dot dot dot, I'm not indicating that there's a relationship that can be continued like in the same way every time. I'm not adding pi to it, in other words. But there are more terms. Okay, so this is what this is what 2 theta would be. So erase that sine part. This is my angle. So the angle itself, 2 theta, is going to be these values. And if I would divide then by 2, I will have negative pi over 12, 7 pi over 12. The next one would be 11 pi over 12, and we would keep going, right? This is what those would look like, something like that. So let's figure it out. Let's chart with the first 2 and see if they give us the right loop. Because some of these are going to give us the big loop, and some of them are going to give us the small loop, and our calculator is going to be able to help us to decide which is which. So I'm going to use the ones that were first mentioned, which was negative pi over 12 now, to 7 pi over 12. And I think that does give me the bigger loop. If you want to manipulate with it just so that you can see, if we had done 7 pi over 12 to 11 pi over 12 and we graphed it, you can see we get one of the little bitty loops. Okay, so the calculator is a good resource for us making sure that we have the values we need for the right loop that it's being described, if there's a difference, which this one there was. So let me put this back in. And it is, in fact, the, oops, I'll write that right down right a second. Sorry, took it out and now I need to put it back in and I'm typoing things. Okay. It is the top one that I shaded. It is the yellow one that's actually on my screen that I'm getting. So these are the 2 that I want for my limits of integration. All right, so my area then is 1/2 the interval from negative pi over 12 to 7 pi over 12. And I have 1 plus 2 sine 2 theta squared d theta. Is that okay for everyone? Okay, this problem's not as concise, it's not as clean as the last one because I have a square of something that's summed, right? I have a square of a square of sums. That's actually what I want. I want the square of a sum. So I need to multiply that out. So this is 1/2 my interval from negative pi over 12 to 7 pi over 12. And then this would be 1 plus 4 sine 2 theta plus 4 sine squared of 2 theta d theta. Okay? It's foiling. Perfect square trinomial. But of course the problem, well, I can take the antiderivative of the 1 just fine. I can take the antiderivative of the 4 sine 2 theta just fine. This square one is my problem, right? So let me give you the other power reducing formula because I don't have them written down for you somewhere else. So we have sine of sine squared of theta. And it's a very similar formula. Let's make sure I've got it right. So we're going to have one half, and it's 1 minus the cosine of double the angle. The other one was 1 plus. The only difference is the sign in the middle. So when I come back down here and I use that then, I'm going to have the 1/2. I've still got my interval from negative pi over 12 to 7 pi over 12. I still have 1. I still have plus the 4 sine theta. None of that changes. But then I actually need to have half of this. So my 4 will get reduced by a factor of 2. So this will become a 2. And then I'm going to have 1 minus the cosine of double my angle, which now is 4 theta. Okay, so everybody see why my 4 became a 2?
2 and 1/2.
Because of the 1/2. Yes. If you need to write it in to see that step, then do that. Yeah, I have space over here, so I'm going to move to the next screen. Okay, we need to clean this up, and then we can do an antiderivative. So, one smaller. So this is 1/2 the interval from negative pi over 12 to 7 pi over 12. I have 1 plus 4 sine of theta plus 2 minus 2 cosine of 4 theta d theta. And I should be able to combine my 1 and my 2. So the first part stays the same. Now I have 3 plus 4 sine theta. That's what I was thinking. I was like, I think I missed a 2 here. 2 theta. 2 theta. It's on the other screen wrong too because I copied that one. 2 theta minus 2 cosine of 4 theta. I'm just fixing my previous screen. Okay. We can do some antiderivatives, right? Okay. So we have some more of those u substitutions that are not very exciting showing up. So the first one, the antiderivative of 3, is 3 theta. All right, now we need the antiderivative of 4 sine of 2 theta. So what is the antiderivative of the sine of 2 theta? Yeah, so we're going to get a negative, and I'm going to get a factor of 1/2, but the 1/2 with the 4 in front will simplify. So I'm going to actually change my 4 to a 2 for the same reason it happened before. And this is negative, so I'm going to change this also to a negative. Oh, that was not what I meant to do. That was. Okay, so this is going to be a negative now, and I'm going to have the sine of the double angle 2 theta here. Didn't mean sine. Cosine is what I meant. Cosine, there we go, of my 2 theta. The antiderivative of sine is negative cosine. Okay, everybody see where all the numbers went? Okay, because we're going to do it again on the next one. So this one is the antiderivative of cosine, though. So the antiderivative of cosine is a positive sign. It's still 1/2 of it, so that 2 in front is going to go away. And it's a positive sign, but there's a negative in the formula, so it's still going to say negative. And this will now become a sine of 4 theta. And I need a 1/2, don't I? There's a 1/2 here. This 4 theta means I'm dividing by 4. I have a factor of 1/4, so the 1/4 with the 2 in the front is going to make a 1/2. And if this bothers you, then feel free to write it out like this. Whoops. Right, 1/4 times 2. The 1/4 is coming from the inside part where I have the u substitution. Either way, we're going to be evaluating this then at 7 pi over 12 and negative pi over 12. It's kind of messy. So I have a 1/2 in front. I have 3 times 7 pi over 12, so that's 21. Or, well, actually, it's 7 pi over 4. Minus 2 cosine, and then it would be pi over 6. 7 pi over 6. And then I have minus the 2, and I will have sine, and then it would be 7 pi over 3. I'm simplifying as I go. If you don't like to simplify as you go, feel free not to simplify as you go. Did I simplify correctly? What did I miss? Oh, yes, right here. Thank you. Okay, everything else okay? Okay, great. And then we're evaluating then at the negative pi over 12. So this would be negative pi over 4 minus 2 cosine of negative pi over 6 minus 1/2 sine of negative pi over 3. think I've closed and opened everything right. Do all those look okay? Man, there's a lot of negatives going on in that second one. We're bound to lose something if we're not real careful. Okay, let's try and get some values here. So we have the 1/2 in front. We have the 7 pi over 4. And I'm going to collect this other piece that's got a pi value over here. This should be plus pi over 4. Everybody good with that one? So I'm going to move that in front with my 7 pi over 4. That's very friendly. Look at that. Those add together nicely. All right, the next one, -2. What is the cosine of 7 pi over 6? We've already drawn that in, but let me remind you. We're down here. That's not good, but it is square root 3 over 2. Is it positive or negative? It's negative. So negative square root 3 over 2. And I have minus 1/2. 7 pi over 3 is otherwise known as what?
Pi over 3.
It's pi over 3, right? 7 pi over 3 is 2 and 1/3 pi. So if you go around all the way around 2 pi, and then you go 1/3 more, you're in the same spot. So this is the same thing right here as really just having pi over 3. So what is the sine of pi over 3? Somebody about to say it. It's wrong, yeah. Square root 3 over 2 is the other one. Yeah, it's square root 3 over 2, and it's positive. We're in quadrant 1, so this is square root 3 over 2. Over here, I have, let me erase that highlighting now. I have this negative that needs to go through to this negative, and that's fine. So that's going to end up being a positive, and it really is going to end up being a positive 2. This cosine of negative pi over 6, this negative pi over 6 right here, you can do negative pi over 6. That's fine. You're just going to go back into quadrant 4. But there's also even and odd identities that tell you that the cosine of negative angles is exactly the same as the cosine of the same positive angles. So the cosine of pi over 6 is the same as cosine of negative pi over 6. You don't have to use that. You can be down in quadrant 4 to do that. That's fine. Either way, what's the cosine value if we're over there? It's another square root 3 over 2. Apparently that's the theme of this problem. We've got one more. So this negative here and this negative here would make that positive, but the negative inside of sine makes it negative, right? Sine is an odd function, so the negative comes out in front. So we've got 3 negatives going on. So this is actually going to be a negative then of the sine of pi over 3. So sine of pi over 3, that one is, that one's 1/2. This is the 1/2 one. We got a 1/2 in one of them. Okay, I think they're all there now. I hope so. Did I get it right? Oh, it's a 1/2 times a 1/2. I was like, there's missing something. Yeah. There's a 1/2 in front, and then we have a 1/2 value. Perfect. Bracket here. All right, this is a mess. 1/2. We have 7 pi over 4 plus pi over 4. That would be 2 pi, right? All right. These are going to be positive. So the 2's are going to cancel. This is just squared 3. And then I have minus square root 3 over 4. I have plus square root 3 again, because the 2's are going to cancel. And then I have minus 1/4. Okay, so the progress is slow, but I think we're making progress. This is kind of a mess. We're not going to be able to clean it up completely, right? It is going to be kind of messy, but we can consolidate everything into one fraction if we wish. I can't remember if I have that written that way on my notes. I have everything that's got the square roots to go, everything that has, okay, I've left the pi out, which makes sense. So if I distribute this through, this piece is pi. Agreed? Oh, that's good. So this is pi. On the other counts, let's see, this is square root 3 and square root 3, which gives me 2 square root 3's, right? So I have 2 square root 3. And then I have minus, and I can combine these pretty nicely together because they're both in over 4 format. So I have a square root of 3. They're both negative 2, so I have a negative in front. And then I can do square root of 3 plus 1 over 4.
Shouldn't that one
Did I get
have
that wrong?
all of them?
Which one half?
The one on the outside. You had to cancel out.
It does, and I haven't put it to it yet. So here's a 2 here, and here's a 2. Will that be good for us? Yeah, thank you. Okay, well, that one will cancel then. That's fine, I suppose. So we have pi plus the square root of 3. And I'm going to get them to have a common denominator. So this would be 8 square root of 3 over 8 minus square root 3 plus 1 over 8. And if I've consolidated it right, which at this point is anybody's guess, because I feel like we had so many negatives going on, but I think that we would have pi plus 7 square root 3 plus a 1 minus a 1 because the negative distribute through over 8. So I moved this negative through here. I'd pulled it out originally, not put it back through. This looks like about as simple as it's going to get, which does not match my notes, which means that there's an error somewhere either in my notes or on the screen.
Sine of negative pi over 3 is square root of 2.
Which one?
Sine of pi over 3 is square root of 2.
It is. And you guys even said that, and I said no, and my notes say it is too, this piece right here, which is probably why here.
Yeah.
Thank you. Okay. Does that put it here? Square root 3 over 4. Let's clean that up and then we'll fix that then. That's 2 of them. So it's negative square root 3 over 2. I have a pi. Square root 3 over 2. So 2 square root 3 over 2 minus square root 3 over 2. It's closer to what my notes say. Does that match? No, I forgot my 4 again because I distributed it through. Good grief. Too many things going on. I'm sorry, guys. This one should be a 4, this one should be a 4, and then I have a 4 at the end. Does that sound right? Maybe?
Yep, that's right.
That's right.
Yeah.
Okay, we're going to go with it. What's wrong?
Should it be a positive?
It should be a positive, yes. That one, I didn't get it fixed. Yes, that one should be a positive. I think we're good. A lot of missing pieces. Pardon me on that one, but yes. Okay, all good. Okay. We can do arc length as well. Okay? So that was area, this is arc length. We put them together a lot of times because their formulas are quite similar. So let f be a function whose derivative is continuous on alpha beta. Same setup as the last one. So beta minus alpha is between 0 and 2 pi. The length of the graph, right? So finding the length of the edge is the arc length s equals from alpha to beta of the function squared plus its derivative squared. Okay? And then square root. Another way to write this is alpha to beta of r squared plus dr d theta squared. And then d theta on the end. Okay, this is a much friendlier problem than the last one. Let's get it done. I think we still have time to do it, probably in the next 2 minutes. So let me just mention that you can find alpha and beta from the graph over here. So alpha and beta are from a graph. We won't belabor that point again. We've done it a couple of times. From the graph, they're actually 0 and 2 pi. Okay. We do need r prime. We need the derivative here. And the derivative of this would be 9 cosine of 3 theta. Everybody good with that? So my arc length, s, is the integral from 0 to 2 pi of the square root of the original equation, which was 2 plus 3 sine of 3 theta squared plus the derivative, which is 9 cosine squared, or cosine of 3 theta squared d theta. If we square things out and clean things up, we're going to end up getting that we have here 4 plus 12 sine 3 theta plus 9 sine squared of 3 theta plus 81 cosine squared of 3 theta.
Why is that 12 cents?
It's 2 times 3 and doubled. Yep, that's the shortcut for it anyway. Here's the deal. You've got a sine squared and a cosine squared, but they don't have the same coefficient. Agreed? I know. Wish they did. That would be so much better. But what we can do is we can consolidate part of them. So we have our 4. We have plus 12 sine of 3 theta. And we can take 9 of those, right? So we can actually be replacing it as 9. If I break this apart as 9 of these and 72 of them. 9 of them are combined and 72 of them are not. Everybody with me? So we're going to have a 9 because we're going to have plus 1 times the 9. And then we have 72 of them still left. 72 cosine squared of 3 theta. Those are the pieces that did not combine using the Pythagorean identity. Okay? It's only 72 of them. It's not that many. That's exactly right. And at this point, we're going to clean up a little bit, but at this point, we would actually need our calculator to do this. So this is 13 plus 12 sine of 3 theta, and we would have our 72 cosine squared of 3 theta. We could use a power reducing formula, and that's fine, but it's not going to get us where we need to go. We're still not going to have a perfect square underneath here that we can take the square root of. Okay, it's not going to happen. We're going to get it as cleaned up as we can, which we did, and so now we're going to use a calculator. Okay? You do this in polar. So let's do it real quick. If you will put in, we don't have time to do it real quick. Let me push pause. I'm going to go back to my office and I will record a second little video that just tells you how you put in your calculator as a reminder. It's not much different than we've done before, but I'll record that for you and I'll post it as a separate video. Okay?